Hello and welcome to Space Historians. I'm so glad you found your way here tonight, ready to slow down, breathe deeply, and let your thoughts drift across the largest question we can ask. Not about a single star, or a galaxy, or even a cluster of galaxies, but about everything, about the universe itself, and whether it will ever stop growing. Tonight, we're not rushing toward answers. We're floating gently through the question, letting it unfold naturally, like the expansion we're exploring. This is your moment to leave the noise behind and step quietly into the vast, patient rhythm of cosmic time. Before we begin our journey, I'd love to know, where in the world are you listening from, and what time is it where you are? It's a small thing, but it reminds me that while we're scattered across this planet under different skies, we're all held within the same expanding universe. We're all moving outward together, carried along by forces we can barely comprehend. If you enjoy these quiet journeys through the deepest questions of existence, a like and a subscribe help keep this channel drifting steadily through the cosmos. And for those who've already joined this constellation of curious minds, thank you. You're part of this voyage, part of this shared wonder. Each episode here isn't just about facts or figures. It's about the feeling of contemplating something so vast that it changes how you see yourself. Tonight's question, when will the universe stop expanding, touches on time, fate, eternity, and our place within it all. So as your breathing slows and your thoughts begin to settle, imagine yourself suspended in the darkness between galaxies. No up, no down, just the gentle pull of space itself, stretching in every direction. The universe has been exhaling since the beginning of time. And you're here, now, riding that breath. If you'd like to be notified when the next journey begins, gently press the notification bell. But for now, you don't need to do anything, except listen, wonder, and drift. Let's travel together, through the deep questions of cosmology, through the patient work of astronomers, through the endless mystery of what comes next. Welcome to the expanding edge of everything. Here's something that sounds impossible, but it's true. Right now, at this very moment, most of the galaxies in the universe are moving away from us. Not just drifting, racing. Some are receding at speeds faster than any rocket, any spacecraft, anything we've ever built could achieve. And the farther away they are, the faster they're fleeing. It's not because they dislike us. It's not because of some cosmic repulsion. It's because the universe itself is expanding. Space, the very fabric of reality, is stretching, and everything in it is being carried along. This discovery changed everything. For most of human history, we believed the universe was static, eternal, unchanging. The stars rose and set with comforting regularity. The constellations looked the same to ancient Greeks as they do to us today. Nothing about the night sky suggested motion on the grandest scale. But in the early 20th century, a few patient observers began to notice something strange. When they analysed the light from distant galaxies, they found a consistent pattern. The light was redder than it should be, not because the galaxies were red, but because their light had been stretched by the expansion of space itself. This effect is called redshift, and it's similar to what happens with sound. When an ambulance rushes past you, its siren drops in pitch as it moves away. The sound waves are stretched. Light does the same thing. When a galaxy moves away from us, its light waves are stretched toward the red end of the spectrum. In 1929, an astronomer named Edwin Hubble made a discovery that would reshape our understanding of everything. He measured the distances to dozens of galaxies and their redshifts. and he found a pattern so clear, so undeniable, that it could only mean one thing. The farther away a galaxy was, the faster it was moving away from us. This wasn't random, it was systematic, it was universal, and it could only be explained one way. The universe was expanding. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move away from each other, not because they're travelling across the surface, but because the surface itself is growing. Every dot sees every other dot moving away. There's no centre to the expansion. Every point is expanding away from every other point. That's what's happening in the universe. Space itself is creating more of itself. Galaxies are not flying through space, they're being carried by space. And because space is expanding everywhere, every observer, no matter where they are in the universe, sees the same thing we do. All distant galaxies appear to be moving away. This realization was staggering. If the universe is expanding now, it must have been smaller in the past. Wind the clock backward, and you reach a moment when everything, every galaxy, every atom, every point of space, was compressed into an infinitesimally small region. From that state, the universe began to expand. That moment, about 13.8 billion years ago, is what we call the Big Bang. The Big Bang wasn't an explosion in space. It was the expansion of space itself. There was no centre, no edge, no before in the way we usually think of it. Time and space came into existence together. The universe didn't expand into something. It created the something as it expanded, and it's never stopped. For nearly 14 billion years, space has been stretching. Galaxies have been drifting apart. The universe has been growing larger and larger and larger. But here's where the story takes a turn. For decades after Hubble's discovery, scientists assumed that gravity would eventually slow the expansion down. After all, everything with mass attracts everything else. The collective gravity of all the matter in the universe should act like a brake, gradually slowing the expansion until it stopped or even reversed. But in the late 1990s, astronomers studying distant supernovae made a discovery that shocked the world. The universe wasn't slowing down. It was speeding up. Imagine throwing a ball into the air and watching it not fall back down, but instead accelerate upward, faster and faster. That's what the universe is doing. The expansion is accelerating. Something is pushing space apart, overpowering the gravitational pull of all the matter in the universe. Scientists gave this mysterious force a name: dark energy, and it makes up about 68% of everything in the universe. We don't know what it is. We don't know why it exists. But we can measure its effect. It's causing the universe to expand faster and faster with every passing moment. This brings us to the question that hangs over everything. If the universe is accelerating, if dark energy is driving galaxies apart at ever-increasing speeds, what happens next? Will the expansion continue forever? Will galaxies drift so far apart that future civilizations will look up and see nothing but darkness? Or is there some limit, some turning point, where the expansion slows, stops, or reverses? The answer depends on things we don't yet fully understand. The nature of dark energy, the total mass of the universe, the geometry of space itself. But cosmologists have developed models, scenarios for how the expansion might unfold over the next billions, trillions, even googles of years. And what they've found is both beautiful and haunting. The universe's fate is not decided. It depends on subtle balances, on forces we can barely detect, on questions at the very edge of our understanding. But one thing is clear: the expansion, the great cosmic drift that began nearly 14 billion years ago, will shape the future of everything. Right now, you're part of that expansion. Not in the sense that your body is stretching, gravity holds you together too tightly for that, but in the sense that you're embedded in an expanding cosmos. The space between galaxies is growing, the universe is getting larger, and you, sitting or lying wherever you are riding along on that slow, patient, unstoppable tide. The universe is running away from itself. Every galaxy is fleeing from every other galaxy. The distances are growing, the light is stretching, and somewhere in the distant future, trillions of years from now, the night sky might be completely dark, every distant light having drifted beyond the edge of what any telescope could ever see. But we're not there yet. We're here, now, at a moment in cosmic history when the sky is still full of stars, when galaxies are still visible, when we can still measure the expansion and ask the question, when will it stop? This is where our journey begins. With that question, with the expanding universe, with the mystery of what comes next, and with you, wondering, as humans have always wondered, what it all means and where it's all going. To understand when, or if, the universe will stop expanding, we first need to understand the stage on which this drama unfolds. We need to see the universe as it is now, billions of years after the Big Bang, shaped by forces both visible and invisible, held in a delicate balance between expansion and collapse. The universe, as best we can observe it, is vast beyond comprehension. It contains at least 2 trillion galaxies, each with hundreds of billions of stars. And that's just the observable universe, the region from which light has had time to reach us since the Big Bang. Beyond that horizon, there may be infinitely more space, infinitely more galaxies, forever beyond our sight. But let's focus on what we can see. The observable universe is a sphere roughly 93 billion light-years across, with us at the center. Not because we're special, but because we can only see light that's had time to reach us. An observer in any other galaxy would see their own observable universe, centered on them. Within this sphere, matter is not distributed evenly. It's organized into a structure called the cosmic web. Galaxies cluster together in groups and superclusters, connected by filaments of gas and dark matter. Between these filaments are vast voids, regions where almost nothing exists. The whole structure looks like foam, with dense regions separated by empty bubbles. This structure formed over billions of years, shaped by gravity. In the early universe, matter was almost perfectly smooth, with only tiny variations in density. But gravity amplified those variations. Denser regions attracted more matter, becoming even denser. Over time, they collapsed into the first stars and galaxies. Less dense regions lost matter and became the voids. The cosmic web is still evolving. Galaxies are still merging. Clusters are still growing. But something else is happening too. The space between clusters is expanding. The filaments are stretching. The voids are growing larger. This is the expansion we're exploring, the slow, patient growth of space itself. Now, let's talk about what fills this space. The universe is made of 3 main components, and their relative amounts determine the fate of the expansion. First, there's ordinary matter. This is the stuff we're familiar with: atoms, molecules, stars, planets, gas, dust. It makes up about 5% of the universe's total energy density. That's right, only 5%. Everything you can see, Everything you've ever touched, every star in the sky, is a tiny fraction of what's out there. Second, there's dark matter. This is a mysterious substance that doesn't emit, absorb, or reflect light. We can't see it directly, but we know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by the gravity of their visible matter alone. There must be something else, something invisible, providing additional gravitational pull. That something is dark matter, and it makes up about 27% of the universe. Third, there's dark energy. This is even more mysterious than dark matter. It's not a substance in the traditional sense. It's a property of space itself, a kind of repulsive force that pushes things apart. Dark energy makes up about 68% of the universe, and it's responsible for the accelerating expansion. These three components, ordinary matter, dark matter, and dark energy, are engaged in a cosmic tug-of-war. Matter, both ordinary and dark, exerts gravity, pulling things together, trying to slow the expansion. Dark energy pushes things apart, trying to accelerate it. The fate of the universe depends on which force wins. For billions of years, matter dominated. Gravity was stronger than the repulsive effect of dark energy. The expansion was slowing down, not speeding up. But about 5 billion years ago, something changed. The universe had expanded enough that matter was spread thin, while dark energy, being a property of space itself, remained constant. Dark energy began to dominate. The expansion began to accelerate. This transition marked a turning point in cosmic history. Before it, the universe was decelerating. After it, accelerating. And if current models are correct, this acceleration will continue forever, with dark energy driving the expansion faster and faster, until galaxies drift beyond the edge of the observable universe and disappear from view. But that's assuming dark energy remains constant. And we don't know if that's true. Dark energy could change over time. It could strengthen, weakening, or even reverse. Each possibility leads to a different fate for the universe. The setting for our story, then, is a universe in transition. A cosmos that spent most of its early history slowing down, only to start speeding up relatively recently. We're living at a special time, cosmologically speaking, a time when the universe is still full of galaxies, still bright with stars, but beginning to accelerate toward a future that's much darker and lonelier. The cosmic stage is also defined by geometry. Einstein's general relativity tells us that space itself can be curved by the presence of matter and energy. Depending on the total density of the universe, space can be flat, like a sheet of paper, closed, like the surface of a sphere, or open, like a saddle. Measurements from satellites like the Wilkinson Microwave Anisotropy Probe and the Planck mission have shown that the universe appears to be flat, at least within the limits of our measurements. This has profound implications. A flat universe, if dominated by dark energy, will expand forever. A closed universe might eventually stop expanding and recollapse. An open universe will expand forever, regardless of dark energy. The geometry, the composition, and the history of the universe all combine to set the stage for the question we're exploring. Will the expansion stop? To answer that, we need to understand not just where we are now, but how we got here and where the forces at play are taking us. The cosmic stage is vast, complex, and dynamic. It's a universe of galaxies and voids, of matter and dark energy, of expansion and gravity locked in an eternal contest. And somewhere within it, on a small planet orbiting an ordinary star, we're watching, measuring, and trying to understand what it all means. This is the setting. This is the arena where the fate of the universe will be decided. And now that we've seen it, we can begin to explore the forces that shape it, the discoveries that revealed it, and the possible futures that await it. The story of how we discovered the expanding universe is a story of light. Not the light we see with our eyes, but the faint, ancient light that has travelled billions of years to reach us, carrying messages from the edge of space and time. In the early 20th century, astronomers had powerful telescopes, but they didn't yet know what they were looking at. When they pointed their instruments at the sky, they saw faint, fuzzy patches of light scattered among the stars. Some astronomers thought these patches, called nebulae, were clouds of gas within our own Milky Way galaxy. Others suspected they might be something more distant, perhaps even separate galaxies. The debate was settled in 1924 when Edwin Hubble, working at the Mount Wilson Observatory in California, observed a type of star called a Cepheid variable in one of these nebulae, the Andromeda Nebula. Cepheids pulse with a regular rhythm, and their brightness is directly related to that rhythm. By measuring the pulse and the apparent brightness, Hubble could calculate the distance, and the distance he found was staggering. Andromeda was far beyond the Milky Way. It was a separate galaxy. This discovery expanded the known universe almost overnight. The cosmos was not just our galaxy, but countless galaxies, each containing billions of stars scattered across unimaginable distances. But Hubble wasn't done. Over the next few years, Hubble measured distances to more galaxies, but he also did something else. He analysed their light using a spectrograph, an instrument that splits light into its component wavelengths. What he found was puzzling. The light from most galaxies was shifted toward the red end of the spectrum. This redshift meant the galaxies were moving away from us. But here's the key discovery. The redshift wasn't random. The farther away a galaxy was, the greater its redshift. The more distant the galaxy, the faster it was receding. This relationship, now called Hubble's law, could only mean one thing. The universe was expanding. Imagine you're standing in a room where everything is moving away from you. The closer objects move slowly. The farther objects move quickly. If that's happening in every direction, it's not that you're special or at the center. It's that the room itself is expanding, carrying everything within it away from everything else. That's what Hubble discovered. The universe was like that room. Space itself was stretching, carrying galaxies along with it, and the effect was the same everywhere. No matter where you stood in the universe, you would see the same pattern of galaxies receding. Hubble published his findings in 1929. The paper was brief, only a few pages, but its implications were enormous. The universe had a history. It had been smaller in the past, and if you traced that expansion backward, you reached a beginning. But Hubble's discovery raised questions. What was driving the expansion? What would happen in the future? Would it continue forever? Or would gravity eventually pull everything back together? For decades, astronomers assumed gravity would slow the expansion. The question wasn't whether it would slow, but by how much. Some models predicted the universe would eventually stop expanding and recollapse in a big crunch. Others predicted it would expand forever, but at an ever-decreasing rate, asymptotically approaching a halt. To find out which was true, astronomers needed to measure how the expansion rate had changed over time. And to do that, they needed to observe very distant galaxies whose light had been travelling for billions of years. The light from those galaxies would show them how fast the universe was expanding in the distant past. and by comparing that to the current rate, they could determine if the expansion was slowing. This required finding very distant, very bright objects that could be used as cosmic mile markers. And in the 1990s, two teams of astronomers found the perfect tool: Type Ia supernovae. Type Ia supernovae are exploding stars that reach a consistent peak brightness. This makes them ideal for measuring cosmic distances. If you know how bright they should be, and you measure how bright they appear, you can calculate how far away they are. And by measuring their redshift, you can determine how fast they're moving away. In the late 1990s, both teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, published their findings. What they found shocked everyone. The distant supernovae were dimmer than expected. That meant they were farther away than they should be if the expansion had been slowing down. The only explanation was that the expansion hadn't been slowing. It had been speeding up. The universe wasn't coasting to a stop. It was accelerating. This discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. But it also raised a profound mystery. What was causing the acceleration? Gravity pulls things together. Something had to be pushing them apart. That something was given a name: dark energy. But naming it didn't explain it. Dark energy is one of the biggest mysteries in modern physics. We know it exists because we can measure its effects, but we don't know what it is, why it exists, or where it comes from. Dark energy appears to be a property of space itself. As space expands, more space is created, and with it, more dark energy. This creates a feedback loop. More space means more dark energy, which causes faster expansion, which creates more space, and so on. If this continues, the expansion will accelerate forever. The discovery of the accelerating expansion changed everything. It meant the universe's future would be very different from what anyone had imagined. Galaxies would drift apart. The night sky would grow darker. Eventually, billions of years from now, distant galaxies would recede so fast that their light could never reach us. They would disappear beyond the cosmic horizon, leaving future observers in isolated island universes. But the discovery also opened new questions. Is dark energy constant, or does it change over time? Could it weaken, strengthen, or even reverse? Each possibility leads to a different fate for the universe. The light from the edge, the ancient photons that travelled billions of years to reach our telescopes, revealed a universe more dynamic and mysterious than we ever imagined. The expansion was not just a relic of the Big Bang. It was an ongoing process, driven by forces we barely understand, shaping the future of everything. This was the discovery. This was the moment when we realized the universe wasn't slowing down. It was speeding up, and that changed the question we're exploring tonight. It's not just, will the universe stop expanding? It's, can it stop, or is it doomed to accelerate forever? When the news broke in 1998 that the universe was accelerating, the scientific community's reaction was swift and stunned. Disbelief, initially. Then awe, then a scramble to understand what it meant. For decades, cosmologists had been working under a clear assumption. Gravity was the dominant force shaping the universe's fate. The Big Bang had set everything in motion, but gravity would eventually slow things down. The debate wasn't about whether the expansion would slow, but about how much. Would it slow enough to stop and recollapse, or would it slow forever but never quite halt? No one, not a single mainstream cosmologist, predicted acceleration. It violated the intuitive understanding of how the universe should behave. Gravity attracts. More matter means more attraction. The universe is full of matter. Therefore, the expansion should slow. But the data didn't lie. The distant supernovae were too dim, meaning they were farther away than expected. The universe had expanded more than it should have if gravity were slowing it down. Something else was at work. The first response from many scientists was skepticism. Could the data be wrong? Could there be systematic errors in the measurements? Dust between us and the supernovae could dim their light, making them appear farther away than they really were. Maybe the supernovae themselves were different in the past, not as standardized as assumed. Both teams checked and rechecked. They analyzed potential sources of error. They looked for alternative explanations, but the conclusion held. The universe was accelerating, and soon independent observations confirmed it. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, showed the same thing. The universe's geometry and composition were consistent with accelerating expansion. As skepticism faded, awe set in. Scientists realized they were staring at a profound mystery. 68% of the universe was made of something completely unknown. Dark energy. It didn't emit light. It didn't interact with matter in any way we could detect. It was invisible, intangible, and yet it was the dominant component of the cosmos. Physicists scrambled to explain it. Theories proliferated. Some suggested dark energy was the energy of empty space itself, a prediction from quantum field theory called vacuum energy. But when they calculated how much vacuum energy there should be, they got a number that was vastly, ridiculously larger than what was observed. The discrepancy was one of the biggest unsolved problems in physics. Others proposed that dark energy wasn't a substance at all, but a modification of gravity. Maybe Einstein's general relativity, which had worked so well for nearly a century, needed adjustment on cosmic scales. Maybe the acceleration wasn't caused by dark energy, but by the way space and time behaved when stretched across billions of light years. Still, others suggested that dark energy might not be constant. It could vary over time or space, strengthening or weakening, changing the fate of the universe in unpredictable ways. This opened the door to exotic scenarios. Big rips, where acceleration becomes so extreme that it tears apart galaxies, stars, and eventually atoms, or reversals, where dark energy turns into dark attraction, pulling everything back together. Among the public, the reaction was different. Most people weren't aware of the discovery at first. It was too technical, too abstract. But as the news filtered through science, journalism, and popular media, a sense of wonder emerged. The universe was not static. It was not even simply expanding. It was accelerating toward a future that was both vast and lonely. Some found this comforting. The universe had a story, a trajectory. It wasn't just sitting there. It was going somewhere, even if that somewhere was an ever-expanding void. Others found it unsettling. The idea that most of the universe was made of something we didn't understand, couldn't see, and couldn't explain, challenged the feeling that we understood the cosmos. Philosophers weighed in too. If the universe was accelerating, driven by dark energy, what did that say about the nature of existence? Was the cosmos indifferent to life, to structure, to meaning? Or was there some deeper principle at work, some reason why dark energy had the exact value it did, not too strong to prevent galaxies from forming, not too weak to prevent acceleration? This question led to discussions of the anthropic principle. The idea that the universe's properties might be finely tuned to allow life to exist. If dark energy were much stronger, galaxies would have been ripped apart before stars could form. If it were much weaker, the universe would have recollapsed before life could emerge. We observe the universe we do because we couldn't exist in most other types of universes. But this explanation felt unsatisfying to many. It seemed like giving up, like saying, things are the way they are because we're here to see them. It didn't explain why dark energy existed, only why we might be able to observe it. Religious and spiritual communities also engaged with the discovery, though in varied ways. Some saw the accelerating expansion as evidence of a creator, a universe designed with specific properties and a specific fate. Others saw it as reinforcing the idea that the cosmos was vast, mysterious and beyond human comprehension, a humbling reminder of our place in the grand scheme. But across all these reactions, scientific, public, philosophical, there was a common thread, recognition that we had entered a new era of cosmology. The universe was not the static, eternal cosmos of ancient philosophy. It was not even the simple expanding cosmos of mid-20th century astronomy. It was something stranger, more dynamic, more mysterious. The discovery of acceleration forced a reckoning. We didn't understand the universe as well as we thought. Most of it, nearly 70%, was made of something we couldn't explain. And that something was determining the universe's fate, driving it toward a future that was radically different from its past. The first response, then, was a mixture of disbelief, awe, and humility. Disbelief that the universe could behave in such an unexpected way, awe at the scale and mystery of dark energy, and humility, recognizing that despite centuries of progress, we were still students of a cosmos that constantly surprised us. But the response didn't stop at awe, it transformed into action. Scientists launched new missions to study dark energy. Telescopes were built to map the universe's expansion history in greater detail. Theoretical physicists developed new models, new equations, new ways of thinking about space, time, and energy. The discovery of the accelerating universe wasn't the end of a story. It was the beginning of a new one. A story about the search for dark energy, the quest to understand the universe's fate, and the question we're exploring tonight. Will the expansion ever stop? The first response was just that. A response. But it set the stage for everything that followed. For decades of research, for new discoveries, for deeper mysteries, and for the realization that the universe was not just expanding, it was accelerating towards something we didn't yet understand. At the heart of the accelerating expansion lies a profound contradiction, one that challenges our intuitions and reveals just how strange the universe truly is. The contradiction is this. The universe contains matter, and matter exerts gravity. Gravity attracts. It pulls things together. Every atom in the universe, every star, every galaxy is pulling on every other atom, star, and galaxy. With all that gravitational attraction, the expansion should be slowing down. It should be decelerating, gradually grinding toward a halt or even reversing. But it's not. It's speeding up. The expansion is accelerating. Something is pushing space apart, overpowering the combined gravitational pull of all the matter in the cosmos. And that something, dark energy, is the exact opposite of what we expect. This contradiction isn't just a scientific puzzle. It's a clash between two fundamental forces that govern the universe: gravity, which we understand relatively well, and dark energy, which remains almost completely mysterious. Let's start with gravity. Einstein's general relativity tells us that mass and energy curve space and time. The more mass you have, the more space curves, and that curvature is what we experience as gravity. Planets orbit stars because the star's mass curves space around it. Galaxies hold together because their combined mass creates a gravitational well. On cosmic scales, gravity should act like a brake on the expansion. Imagine throwing a ball into the air. Gravity pulls it back down, slowing its ascent until it stops and falls. The same should happen with the universe. The Big Bang threw everything outward, but gravity should be pulling it back, slowing the expansion over time. For most of the universe's history, that's exactly what happened. In the first few billion years after the Big Bang, gravity dominated. The expansion was slowing. Galaxies were not accelerating away from each other, they were decelerating. The rate of expansion was decreasing. But about 5 billion years ago, something changed. The universe had expanded enough that matter was spread thin. The gravitational attraction between distant galaxies weakened, and dark energy, which had always been there but had been overpowered by gravity, began to dominate. Dark energy is fundamentally different from matter. Matter dilutes as the universe expands. Spread the same amount of matter over a larger volume, and its density decreases. But dark energy doesn't dilute. It's a property of space itself. As space expands, more space is created, and with it, more dark energy. The energy density remains constant, or possibly even increases. This creates an asymmetry. Over time, matter becomes less influential, dark energy becomes more influential, and once dark energy takes over, the expansion begins to accelerate. The contradiction, then, is that the universe is fighting itself. Gravity wants to pull things together. Dark energy wants to push them apart, and currently, dark energy is winning. But here's where it gets even stranger. We don't know what dark energy is. The most common hypothesis is that it's vacuum energy, the energy inherent in empty space due to quantum fluctuations. Quantum field theory predicts that even a perfect vacuum isn't truly empty. It's full of virtual particles popping in and out of existence, creating a baseline level of energy. But when physicists calculate how much vacuum energy there should be, they get an answer that's absurdly large. About 10 to the power of 120 times larger than the observed dark energy. This is called the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. Why is the observed dark energy so much smaller than predicted? Is our calculation wrong? Is our understanding of quantum field theory incomplete? Or is something else going on, some mechanism that cancels out most of the vacuum energy, leaving only a tiny residue? No one knows. And that's the contradiction. We can measure dark energy's effects. We can see it driving the expansion. But we can't explain it. We don't know where it comes from, why it has the value it does, or whether it will remain constant. And if dark energy changes over time, the contradiction deepens. Imagine if dark energy isn't constant, but is instead a field that evolves, a kind of cosmic fluid that can strengthen or weaken. This field is sometimes called quintessence, after the ancient concept of the fifth element. If dark energy is quintessence, its behavior over time depends on its properties. It could remain steady, maintaining the current acceleration. It could weaken, allowing gravity to regain dominance and slow the expansion. Or it could strengthen, accelerating the expansion faster and faster until space itself tears apart. Each scenario leads to a radically different fate for the universe. A steady dark energy means eternal acceleration, with galaxies drifting out of view. A weakening dark energy could lead to a big crunch, where the universe recollapses. A strengthening dark energy could lead to a big rip, where even atoms are torn apart by the expansion. The contradiction, then, is not just about what's happening now, it's about what will happen in the future. The universe's fate hangs on the nature of dark energy, and we don't understand it. There's also a philosophical dimension to the contradiction. For centuries, humans have sought to understand the universe as a coherent, comprehensible system. We've developed laws of physics that explain everything from the motion of planets to the behavior of atoms. But dark energy challenges that. It's a reminder that the universe might not be as comprehensible as we hoped. Some physicists find this thrilling. It means there are still deep mysteries to solve, fundamental questions about the nature of space, time, and energy. Others find it frustrating. After decades of progress, we're confronted with something that seems beyond our current understanding. But the contradiction also reveals something profound about the universe. It's not simple. It's not straightforward. It's full of competing forces, strange properties, and behaviors that defy intuition. The universe is not designed for our understanding. It simply is. And part of being a scientist, or a curious human, is accepting that and continuing to explore, even when the answers are elusive. The contradiction at the heart of the accelerating expansion, gravity versus dark energy, attraction versus repulsion, is not just a scientific problem. It's a window into the deeper strangeness of reality. It shows us that the cosmos is weirder, more mysterious, and more fascinating than we ever imagined. And it brings us back to the question, will the universe stop expanding? To answer that, we need to resolve the contradiction. We need to understand dark energy. We need to know whether it's constant, whether it will change, and whether gravity will ever regain control. The contradiction is real. The universe is pulling against itself. And which force wins will determine the fate of everything. When scientists try to predict the future of an accelerating universe, they develop theories, mathematical models, and scenarios that explore what might happen over vast spans of time. These are not wild speculations. They're based on observations, on the laws of physics, on the best understanding we have of dark energy and the cosmos. But because we don't fully understand dark energy, multiple theories exist, each painting a different vision of the universe's ultimate fate. Some are familiar, others are strange, almost unsettling. Together, they form a spectrum of possible endings, from eternal expansion to violent destruction. The first and most widely accepted theory is the Big Freeze, also called heat death. In this scenario, dark energy remains constant, driving the expansion forever. Galaxies continue to drift apart. Over billions of years, star formation slows as gas is used up. Existing stars burn out, leaving behind white dwarfs, neutron stars, and black holes. The universe grows darker and colder. Eventually, trillions of years from now, the last stars fade. Galaxies become graveyards of dead stellar remnants. Even black holes evaporate through Hawking radiation, a process so slow that it takes 10 to the power of 100 years. In the end, the universe becomes a cold, dark, nearly empty expanse, with particles spread so thin that they almost never interact. This is the heat death, a state of maximum entropy where no energy is available to do work. The universe doesn't end with a bang, it fades into silence. The second theory is the Big Crunch. This requires dark energy to weaken or reverse over time. If that happens, gravity regains dominance. the expansion slows, stops, and reverses. Galaxies begin to move toward each other. Over billions of years, they collide and merge. The cosmic web collapses inward. As space contracts, it heats up. The cosmic microwave background radiation, now stretched and cooled by expansion, becomes compressed and hot. Eventually, temperatures rise so high that stars evaporate and atoms are torn apart. The universe collapses into a state similar to the Big Bang, but in reverse. Everything is crushed into a singularity. This is the Big Crunch, and it might, in some theories, lead to a new Big Bang, a cyclic universe where expansion and contraction repeat eternally. The third theory is the Big Rip. This occurs if dark energy strengthens over time. Instead of remaining constant, it grows, accelerating the expansion faster and faster. At first, the effects are subtle. Galaxies drift apart more quickly. But as dark energy strengthens, it begins to overpower not just the gravitational attraction between galaxies, but the forces holding galaxies themselves together. Eventually, dark energy becomes so strong that it tears apart galaxy clusters, then galaxies, then solar systems, then planets, then atoms. The fabric of space stretches so violently that everything is ripped apart. This happens at a specific moment, perhaps 50 billion years in the future, when dark energy reaches a critical strength. The Big Rip is sudden, violent, and total. The universe doesn't fade, it's torn to shreds. The fourth theory is the Big Bounce. This is related to the Big Crunch, but instead of ending in a singularity, the universe rebounds. Some versions of quantum gravity suggest that space can't collapse beyond a certain density. At that point, quantum effects take over, and the collapse reverses into a new expansion. The Big Bounce creates a cyclic universe, where each cycle begins with a Big Bang and ends with a Big Crunch, which immediately becomes the next Big Bang. This theory is appealing because it avoids the problem of an ultimate beginning or end. The universe has always existed and always will, cycling through phases of expansion and contraction. A fifth, more speculative theory involves vacuum decay. In quantum field theory, our universe might be in a metastable state, like a ball balanced on a hill. It's stable for now, but a small disturbance could send it rolling into a lower energy state. If that happens, a bubble of true vacuum would form, expanding at the speed of light, destroying everything in its path. The laws of physics inside the bubble would be different. Atoms might not exist. Stars might not shine. This transition could happen at any time, without warning, rendering the universe as we know it non-existent. Fortunately, this is considered unlikely, but it can't be ruled out entirely. Each of these theories depends on the nature of dark energy. If it's a cosmological constant, a true constant that never changes, the Big Freeze is most likely. If it's quintessence, a dynamic field that evolves, the Big Crunch or Big Rip becomes possible. If quantum effects dominate at extreme densities, the Big Bounce might occur, but these theories also depend on other unknowns. The total mass of the universe, the properties of dark matter, the behavior of space and time at extreme scales. Small changes in these parameters can lead to vastly different outcomes. For now, observations favor the Big Freeze. Dark energy appears to be constant, or close to it. The universe is accelerating at a steady rate. If this continues, galaxies will drift beyond the cosmic horizon, the night sky will go dark, and the universe will expand forever, cooling toward absolute zero. But we can't be certain. Our observations only cover a tiny fraction of cosmic history. We're looking at the universe as it is now, about 13.8 billion years after the Big Bang. That's less than 1% of the time the universe might exist. The future could hold surprises we can't yet imagine. The theories, then, are not predictions. They're possibilities, explorations of what might happen if certain conditions hold. They're humanity's attempt to look forward across billions and trillions of years to imagine the ultimate fate of everything. And they're humbling. Whether the universe ends in a freeze, a crunch, a rip, or a bounce, the timescales involved dwarf human comprehension. The differences between these scenarios won't matter for billions of years. By the time the universe's fate is sealed, humanity, if it still exists, will have evolved beyond recognition. The sun will have died, the earth will be gone. Civilizations will have risen and fallen countless times. Yet we ponder these endings now, driven by curiosity, by the need to understand, by the recognition that we're part of something larger than ourselves. The theories of the universe's end are not just scientific, they're existential. They force us to confront the temporary nature of everything, including ourselves. But they also reveal the universe's grandeur. The fact that we can even ask these questions, that we can develop theories and test them, that we can look across billions of years and imagine the future, is itself extraordinary. We are the universe contemplating its own fate. The theories exist, multiple visions of the end. And the question remains, which one is true? Will the universe stop expanding, reverse, or accelerate forever? The answer, hidden in the nature of dark energy, is one of the deepest mysteries we face. Understanding the fate of the universe requires measuring something we can't see, interact with, or directly detect. Dark energy, and yet, over the past few decades, scientists have developed ingenious ways to study it, using light, distance, and time as their tools. The investigation began with supernovae. In the 1990s, the discovery that distant Type Ia supernovae were dimmer than expected revealed the accelerating expansion. But that was just the beginning. To understand dark energy, scientists needed more data, more precise measurements, and observations spanning greater distances and timescales. New telescopes were built or repurposed for this task. Ground-based observatories scanned the sky for supernovae, detecting hundreds and eventually thousands. Space telescopes like Hubble provided high-resolution images and spectra, free from the blurring effects of Earth's atmosphere. One major project was the Supernova Legacy Survey, which used the Canada-France-Hawaii telescope to discover and study supernovae in the distant universe. Over 5 years, it observed over 500 high-redshift supernovae, providing a detailed map of the universe's expansion history. The data confirmed the acceleration and constrained the properties of dark energy. But supernovae weren't the only tool. Cosmologists turned to the cosmic microwave background, the faint radiation left over from the Big Bang. This light, emitted when the universe was only 380,000 years old, carries information about the universe's composition, geometry, and evolution. Satellites, like the Wilkinson Microwave Anisotropy Probe and Planck, mapped the cosmic microwave background in exquisite detail. They measured tiny temperature fluctuations, imprints of density variations in the early universe. By analyzing these fluctuations, scientists could determine the total energy density of the universe and how much of it was dark energy. The results from the cosmic microwave background matched the results from supernovae. About 68% of the universe's energy was dark energy. The universe was flat, meaning its geometry was consistent with eternal expansion. and the dark energy appeared to behave like a cosmological constant, a property of space that didn't change over time. Another method involved studying the large-scale structure of the universe, the distribution of galaxies across cosmic space. Gravity causes matter to clump together, forming the cosmic web of filaments and voids, but dark energy opposes this clumping, smoothing out the distribution of galaxies over time. By mapping how galaxies are distributed, scientists could infer the influence of dark energy. Projects like the Sloan Digital Sky Survey catalogued millions of galaxies, measuring their positions and redshifts. By analysing patterns in this distribution, cosmologists could test models of dark energy and constrain its properties. The data showed that dark energy had been influencing the universe's structure for billions of years, consistent with a cosmological constant. A fourth method involved baryon acoustic oscillations, subtle ripples in the distribution of galaxies caused by sound waves in the early universe. These ripples left a characteristic scale in the cosmic web, a standard ruler that could be used to measure distances and the expansion rate. By comparing this ruler at different times in cosmic history, scientists could track how the expansion had evolved. All these methods pointed to the same conclusion. Dark energy was real. It was causing the universe to accelerate, and it appeared to be a cosmological constant or something very close to it. But the investigation also revealed uncertainties. Dark energy's equation of state, the relationship between its pressure and energy density, was crucial for predicting the universe's fate. If the equation of state was exactly -1, dark energy was a true cosmological constant, and the universe would expand forever. If it was slightly different, dark energy might evolve over time, leading to a big crunch, big rip, or some other outcome. Current measurements put the equation of state very close to -1, but not exact. The uncertainty leaves room for alternative models. Dark energy might be quintessence, a dynamic field that changes over time. Or it might be a sign that general relativity breaks down on cosmic scales, requiring a new theory of gravity. To resolve these questions, new missions were planned. The Dark Energy Survey, using a telescope in Chile, mapped hundreds of millions of galaxies, studying their distribution and the effects of gravitational lensing, where dark matter and dark energy bend light from distant sources. The European Space Agency's Euclid mission, launched in 2023, is designed to map the geometry of the universe and trace dark energy's influence over 10 billion years of cosmic history. NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will use supernovae, gravitational lensing, and baryon acoustic oscillations to study dark energy with unprecedented precision. These missions aim to measure dark energy's properties to within 1%, providing a definitive answer about whether it's truly a constant or something more exotic. The investigation of dark energy is also pushing the boundaries of physics. Theorists are developing new models that might explain it. Some propose modifications to general relativity, such as fur, gravity, or brane-world scenarios, where our universe is a four-dimensional membrane in a higher dimensional space. Others explore quantum field theory, looking for mechanisms that could explain why vacuum energy is so much smaller than predicted. There are also experiments searching for dark energy on smaller scales. Some theories suggest dark energy might interact weakly with matter, creating forces that could be detected in laboratories. Atom interferometers, which measure the effects of forces on atoms with incredible precision, are being used to search for these interactions. So far, no direct detection has been made, but the search continues. The investigation of dark energy is one of the grand scientific endeavours of our time. It involves observations spanning billions of light years, theoretical work at the cutting edge of physics, and instruments that push the limits of technology. And it's driven by a single question. What is dark energy, and what will it do to the universe? The answer, when it comes, will determine the fate of everything. It will tell us whether the universe will expand forever, whether galaxies will disappear beyond the horizon, whether the night sky will go dark. It will reveal whether we live in a cosmos with a predetermined end or one full of surprises yet to come. The investigation continues. New data is collected, new theories are proposed, and slowly, piece by piece, we're assembling a picture of the universe's future. Measuring the invisible is painstaking work, but it's work that connects us to the deepest mysteries of existence, to the question of when, or if, the universe will stop expanding. Science is built on numbers, on measurements precise enough to distinguish between theories and reveal the hidden structure of reality. And when it comes to understanding the universe's expansion, the numbers are both staggering and delicate, spanning scales from the quantum to the cosmic. Let's start with the Hubble constant, the number that describes how fast the universe is expanding. It's named after Edwin Hubble, who first measured it in 1929. The Hubble constant tells us the rate at which galaxies are receding per unit distance. The current best measurements put it at about 70 kilometers per second per megaparsec. What does that mean? A megaparsec is about 3.3 million light years. So for every 3.3 million light years of distance, galaxies are moving away from us about 70 kilometers per second faster. A galaxy 10 megaparsecs away is receding at 700 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,000 kilometers per second. The farther away, the faster the recession. But there's a problem. Different methods of measuring the Hubble constant give slightly different results. Observations of the cosmic microwave background suggest a value around 67 kilometers per second per megaparsec. Observations of nearby supernovae and other distance indicators suggest 73. The difference is small, but it's statistically significant. This discrepancy is called the Hubble tension, and it's one of the biggest puzzles in cosmology. Why does it matter? Because the Hubble constant is tied to the universe's age, composition, and expansion history. If different methods give different values, either our measurements are wrong, or our understanding of the universe is incomplete. Resolving the Hubble tension might require new physics, new particles, or modifications to the standard model of cosmology. Another crucial number is the density parameter, omega, which describes how much matter and energy the universe contains compared to the critical density needed to keep space flat. Measurements show that omega is very close to 1, meaning the universe is nearly flat. But omega is divided into components. About 5% is ordinary matter, about 7% is dark matter, and about 68% is dark energy. These numbers are not arbitrary. They're derived from observations of the cosmic microwave background, the large-scale structure of galaxies, and the properties of supernovae. And they have profound implications. If omega were significantly different, the universe would have a different geometry, a different expansion history, and possibly a different fate. Then there's the equation of state of dark energy, usually denoted W. This number describes the relationship between dark energy's pressure and its energy density. For a cosmological constant, W equals -1. For quintessence or other evolving fields, W could be different. Current measurements constrain W to be very close to -1. but not exactly. The uncertainty leaves room for models where dark energy changes over time. If W is less than -1, dark energy is growing stronger, leading to a big rip. If W is greater than -1, dark energy could weaken, possibly allowing a big crunch. The exact value of W determines the universe's ultimate fate, and measuring it precisely is one of the main goals of modern cosmology. Another set of numbers comes from the age of the universe. By measuring the expansion rate and tracing it backward, we can estimate when the Big Bang occurred. The current best estimate is 13.8 billion years, give or take a few tens of millions of years. This age is consistent with the ages of the oldest stars and the cooling of the cosmic microwave background. But this number also depends on the universe's composition. If dark energy were different, the expansion history would change, and so would the age. The fact that different methods, stellar ages, cosmic microwave background, expansion measurements, all converge on the same age is a powerful confirmation that our models are on the right track. Then there are the numbers describing the future. If dark energy remains constant, the universe will continue to accelerate forever. In about 150 billion years, all galaxies outside our local group will have receded beyond the cosmic horizon, their light stretched so much that it can never reach us. The observable universe will shrink, containing only the Milky Way and its nearest neighbours. In 1 trillion years, star formation will have largely ceased. Existing stars will burn out. The universe will grow darker. In 10 to the 14 years, stars like the Sun will have exhausted their fuel. In 10 to the 20 years, brown dwarfs and the last low-mass stars will fade. In 10 to the 40 years, even the longest-lived stars, the smallest red dwarfs, will die. By 10 to the 60 years, galaxies will have dispersed. Stellar remnants, white dwarfs, neutron stars, black holes will drift apart, isolated in the expanding void. In 10 to the 100 years, black holes will have evaporated through Hawking radiation. All that remains will be a thin soup of particles, photons, neutrinos, scattered across an unimaginably vast space. These numbers are estimates, extrapolations based on our current understanding. But they give a sense of scale, of the timescales on which the universe evolves. The difference between 1 billion years and 1 trillion years is almost incomprehensible, and yet both are tiny compared to the timescales on which the universe's ultimate fate unfolds. The data also includes information from gravitational waves, ripples in space and time caused by massive objects like merging black holes. Observatories like LIGO and Virgo have detected dozens of these events, and future detectors might use them to study the universe's expansion. Gravitational waves travel at the speed of light, and their journey through expanding space stretches their wavelength, just like light. By measuring this stretch, scientists can infer the expansion rate independently of other methods. Another source of data is quasars, incredibly bright objects powered by supermassive black holes in the centers of distant galaxies. Quasars are so luminous that they can be seen across most of the observable universe. By studying their spectra, astronomers can measure the expansion rate at different epochs, tracing how dark energy's influence has grown over time. All this data, from supernovae, cosmic microwave background, large-scale structure, gravitational waves, quasars, forms a web of evidence supporting the standard model of cosmology. The universe is expanding, accelerating, dominated by dark energy. But the data also reveals gaps, questions, tensions. The Hubble tension, the nature of dark energy, the precise value of W. These are not just uncertainties. they're hints that something deeper is waiting to be discovered. Numbers from eternity, measurements spanning billions of years, pointing toward futures trillions of years away. This is the data that frames our question. Will the universe stop expanding? The numbers say no, not if dark energy remains constant. But they also say we don't know everything. There's room for surprises, for new physics, for outcomes we haven't imagined. The data is our map, our guide through the vastness of cosmic time. And as more data comes in, as measurements become more precise, we inch closer to understanding the ultimate fate of everything. Beneath the question of whether the universe will stop expanding lies a deeper mystery, one that has haunted philosophers and scientists for centuries. Why is there something rather than nothing? This might seem unrelated to expansion and dark energy, but it's not. The fact that the universe exists, that it expands, that it contains matter and energy and structure, is not a given. It's a profound mystery, and understanding expansion forces us to confront that mystery. Start with the Big Bang. About 13.8 billion years ago, the universe began. But what does that mean? Did something come from nothing? Did time itself begin? What, if anything, existed before? These questions push the limits of physics. General relativity breaks down at the moment of the Big Bang, where densities and temperatures approach infinity. Quantum mechanics, which governs the very small, might play a role, but we don't have a complete theory of quantum gravity to describe what happens at such extremes. Some theories propose that the universe didn't come from nothing, but from a previous state. The Big Bounce scenario suggests an earlier universe collapsed, then rebounded into our current expansion. Eternal inflation proposes that our universe is one of countless bubble universes, each with its own Big Bang, budding off from an eternally inflating multiverse. But these theories don't answer the deeper question. Why does anything exist at all? Why is there a multiverse? Why are there laws of physics? Why is there something rather than nothing? One approach is the anthropic principle. The universe has the properties it does because if it didn't, we wouldn't be here to observe it. If dark energy were much stronger, galaxies would never have formed. If it were much weaker, the universe might have recollapsed before life could arise. We find ourselves in a universe compatible with our existence, not because it was designed that way, but because we couldn't exist in most other types of universes. This explanation feels circular to some. It explains why the universe is compatible with life, but not why the universe exists in the first place. Yet it highlights an important point. The universe's properties, its expansion rate, its dark energy, its matter content, are finely tuned in a way that allows complexity, structure, and life. Change any of these properties significantly, and the universe would be vastly different, possibly sterile. Another approach involves quantum mechanics. In quantum field theory, particles can spontaneously appear and disappear due to fluctuations in the vacuum. Some physicists have speculated that the entire universe might be a quantum fluctuation, a region of space and time that spontaneously arose from the quantum vacuum and began to expand. But this raises the question, why is there a quantum vacuum? Why are there quantum fields? We've pushed the mystery back a step, but we haven't resolved it. There's also the possibility that the question itself is flawed. Why is there something rather than nothing? Assumes that nothing is a coherent concept, a state that could exist. But in physics, nothing is notoriously difficult to define. Even empty space is full of quantum fields, virtual particles, and the potential for existence. True nothingness might be impossible. Some philosophers argue that existence is necessary, that something is the default state and nothing is the anomaly. If nothingness is unstable or impossible, then existence is inevitable. The universe exists because non-existence isn't an option. These are deep waters, and we're far from solid ground. But the question matters because it frames everything else. If the universe is contingent, if it could have not existed, then its properties, including its expansion, are contingent too. Dark energy, the accelerating expansion, the fate of the cosmos, all depend on the specific configuration of physical laws and constants that define our universe. But if the universe is necessary, if existence is inevitable, then perhaps its expansion and ultimate fate are also inevitable, written into the structure of reality itself. The deeper mystery also touches on meaning. If the universe will expand forever, if it will eventually become a cold, dark, empty void, does that render everything meaningless? If all stars will die, all galaxies will drift out of view, all structure will dissolve, what's the point? This is the existential dimension of the expansion. It forces us to confront the finite nature of existence, not just our own individual lives, but the existence of everything. The stars, the galaxies, the universe itself, all temporary, all headed toward an end, whether it's a freeze, a crunch, or a rip. But there's another way to see it. Meaning doesn't require permanence. A song doesn't lose its beauty because it ends. A sunset doesn't lose its value because it fades. The fact that something is temporary can make it more precious, not less. The universe is unfolding. It's creating complexity, structure, life, consciousness. And even if it all eventually ends, even if the expansion carries everything toward a silent, dark future, the fact that it happened at all is extraordinary. You are here, now, part of this unfolding. You're a way for the universe to know itself, to experience itself, to reflect on its own existence. The deeper mystery, then, is not just why the universe exists, but why it's the kind of universe that can produce beings capable of asking that question. Why does the universe create complexity? Why does it give rise to life, to consciousness, to curiosity? We don't have answers, but the questions themselves are part of the universe's self-discovery. By wondering, you're participating in the process of existence becoming aware of itself. And that, in some way, is a kind of answer. The universe expands, it evolves, it creates and destroys, and through you, it asks why. The deeper mystery is not separate from the question of expansion. It's intertwined with it, part of the same quest to understand what exists, how it works, and what it means. The expansion of the universe is not just a physical process. It's a manifestation of existence itself, of the fact that there is something rather than nothing, and that something is dynamic, evolving, creating new possibilities with every passing moment. When will the universe stop expanding? Perhaps never, but even if it expands forever, the deeper mystery remains. Why is there anything to expand? Why does existence exist? These questions might not have answers, but asking them is part of what it means to be human, to be conscious, to be part of the universe looking back at itself and wondering. The deeper mystery is the foundation of everything, and as we explore the fate of the expansion, we're also exploring the nature of existence itself. There was a moment in the universe's history when everything changed. Not a dramatic event like a supernova or a galaxy collision, but a quiet transition, a tipping point when one force yielded to another. About 5 billion years ago, dark energy became the dominant force shaping the cosmos. Before that moment, the universe's expansion was slowing down. Gravity, the attractive force between all matter, was pulling galaxies closer together, fighting against the outward momentum of the Big Bang. The expansion continued, but at a decreasing rate. The universe was decelerating, but dark energy was always there, even in the early universe. It just wasn't strong enough to matter. Matter, both ordinary and dark, dominated. The universe was denser then, and gravity was stronger. Dark energy's repulsive effect was overpowered, a whisper drowned out by gravity's pull. As the universe expanded, matter spread out. The density decreased, gravity's strength weakened with distance. But dark energy didn't dilute. It's a property of space itself, and as space expanded, more dark energy appeared. The energy density remained constant. This created a race between two forces: gravity, weakening as matter spread thin; dark energy, maintaining its strength. And about 5 billion years ago, they crossed. Dark energy overtook matter. The expansion stopped decelerating and began to accelerate. This turning point was not sudden in human terms. It took millions of years, a gradual transition invisible to any observer. But in cosmic terms, it was a profound shift. The universe's fate changed. Before the turning point, it was possible, depending on the total mass, that the universe might eventually recollapse. After the turning point, that possibility vanished. The universe was committed to eternal expansion. We're living in the aftermath of that transition. We're in the era of dark energy dominance. The expansion is accelerating. Galaxies are drifting apart faster now than they were in the past, and if dark energy remains constant, this acceleration will continue forever. But the turning point raises questions. Why did it happen when it did? Why did dark energy begin to dominate 5 billion years ago, and not earlier or later? This is called the coincidence problem, and it's one of the puzzles of dark energy. The coincidence is this: the turning point occurred relatively recently in cosmic history. The universe is about 13.8 billion years old. Dark energy took over about 5 billion years ago. That means we're living just a few billion years after the transition, a tiny fraction of the universe's total lifespan. If the universe will exist for trillions of years or more, why are we here at this particular moment, so close to the turning point? It seems like an extraordinary coincidence, unless perhaps it's not a coincidence at all. One explanation involves the anthropic principle. Complex life requires stars, and stars require galaxies, and galaxies require a certain balance of forces. If dark energy had dominated much earlier, galaxies wouldn't have had time to form. If it had dominated much later, intelligent life might have emerged in a very different universe. We find ourselves near the turning point because that's the era when life is most likely to exist. But this explanation feels unsatisfying. It doesn't explain why dark energy has the value it does, only why we might observe it at this stage. It's a reminder that we're still missing something fundamental about dark energy, about why it exists and why it behaves the way it does. The turning point also marks a shift in the universe's story. Before it, the universe was shaped by the struggle between expansion and gravity, between the outward momentum of the Big Bang and the inward pull of matter. Stars formed, galaxies clustered, structure grew, the universe became more complex. After the turning point, that process began to reverse. Acceleration started to dominate. The cosmic web, the filaments and clusters of galaxies, stopped growing. In the far future, It will begin to dissolve as space expands faster than gravity can pull things together. This means we're living in a special time, cosmologically speaking. We're in the era when the universe is still full of structure, when galaxies are still forming stars, when the night sky is still bright. Billions of years from now, observers in distant galaxies, if any exist, will see a very different universe. Most galaxies will have drifted beyond the horizon, the sky will be darker, the universe will appear lonelier. The turning point also has implications for the search for life. If complex life requires a universe with galaxies, stars and planets, then there's a window of time when such life can exist. Before the turning point, the universe was too young, too chaotic. After a certain point in the future, the universe will be too old, too dispersed. Life might be a temporary phenomenon, existing only in the middle chapters of the universe's story. We're in one of those middle chapters. The turning point is behind us. The acceleration has begun. And the question we're exploring, will the universe stop expanding, has been answered, at least provisionally. No, it won't. Not unless dark energy changes. But the turning point also reminds us that the universe is not static. It evolves. Forces rise and fall. What was once insignificant can become dominant, and what seems permanent can be temporary. The universe 5 billion years ago was different from today. The universe 5 billion years from now will be different again. The turning point was the moment when the future became clear, at least in broad strokes. The universe is accelerating. Galaxies are drifting apart. The expansion will continue, possibly forever. And we, living just after the transition, are witnesses to a universe in transformation, a cosmos shifting from one era to another. Understanding the turning point helps us see the bigger picture. The expansion is not just a single process, but a story with chapters. The early universe, dominated by radiation. The middle universe, dominated by matter. The current universe, dominated by dark energy. Each era shaped by different forces, each with its own characteristics. We're living at the boundary between eras. The matter-dominated era is fading into the past. The dark energy-dominated era stretches into the future. And the turning point, 5 billion years ago, was the hinge on which everything turned. This is the moment that sealed the universe's fate, or at least shaped it. The moment when dark energy took over, when acceleration began, when the expansion shifted from slowing down to speeding up. It's a turning point not just in the universe's history, but in our understanding of it. Because once we realized it had happened, we knew the future would be very different from the past. The universe crossed a threshold. And we're on the other side now, carried along by dark energy, moving toward a future that's vast, dark, and profoundly lonely, but also full of mystery, full of questions still to answer, full of the universe's slow, patient unfolding. The acceleration of the universe is not just an abstract concept. It has real, profound consequences for the structure of the cosmos, for the fate of galaxies, and ultimately for the future of life itself. The most immediate consequence is that galaxies are drifting apart. Not the galaxies in our local neighborhood. Gravity holds those together, but distant galaxies, those outside our local cluster. As space expands between us and them, they're receding faster and faster. And because the expansion is accelerating, their speed is increasing. Eventually, these galaxies will recede so fast that their light can no longer reach us. They'll cross the cosmic horizon, the boundary beyond which light cannot travel fast enough to overcome the expansion of space. Once a galaxy crosses that horizon, it's gone. We'll never see it again. No signal, no light, no information from it will ever reach us. This process is already beginning. Galaxies at the edge of the observable universe are receding at speeds close to the speed of light. In the far future, more and more galaxies will cross the horizon. The observable universe will shrink. The night sky will grow darker. In about 150 billion years, all galaxies outside our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies, will have disappeared. An observer at that time would look up and see only a handful of nearby galaxies. The rest of the universe would be invisible, hidden beyond the ever-expanding horizon. This has profound implications. Future civilizations, if they exist, won't be able to see the full universe. They won't know about the billions of other galaxies that once filled the sky. They won't have the data to discover the Big Bang or measure the expansion. Their cosmology will be limited to what they can observe. A tiny island of galaxies in an otherwise empty cosmos. But the consequences go deeper. As galaxies drift apart, the cosmic web, the large-scale structure that connects them, will dissolve. The filaments and clusters that span hundreds of millions of light-years will stretch and thin. The voids will grow larger. The universe will become more uniform, more homogeneous, losing the structure that makes it interesting. Star formation will also be affected. Galaxies form stars from gas, and that gas is replenished over time by accretion from the intergalactic medium. But as space expands, the intergalactic medium thins out. Less gas is available. Star formation slows. Eventually, it stops. In our own galaxy, the Milky Way, star formation will continue for trillions of years, using up the gas that's already here, but eventually that gas will be exhausted. No new stars will form. The galaxy will grow darker as existing stars burn out and die. This process is slow, unimaginably slow by human standards. But it's inevitable. The universe is moving toward a state where star formation ceases, where galaxies become graveyards of dead stars, where the bright, vibrant cosmos we see today becomes a cold, dark expanse. But there's another consequence, one that's more subtle but equally profound. The expansion affects time itself. As space expands, light travelling through it is stretched. This stretching, called redshift, increases the wavelength of the light and decreases its energy. By the time light from a distant galaxy reaches us, it might have been stretched from ultraviolet to visible to infrared, or even further. This stretching affects more than just light. It affects any signal travelling through space. It means that communication with distant galaxies becomes harder and harder, not just because they're far away, but because the signals are weakened and distorted by the expansion. In the far future, even if civilizations exist in other galaxies, they won't be able to communicate with each other. The expansion will have carried them too far apart. Each will be isolated, alone in its own island universe, with no knowledge of the others. This isolation is one of the most haunting consequences of the accelerating expansion. It means the universe is becoming fragmented, divided into regions that can never interact. It's as if the cosmos is breaking apart, not violently, but quietly, through the simple act of expansion. But even within our own local group of galaxies, there are consequences. The Milky Way and Andromeda are currently moving toward each other, pulled by mutual gravity. In about 4 billion years, they'll collide and merge, forming a new, larger galaxy. This process is unaffected by dark energy because gravity is strong enough to overcome expansion on these small scales. But after the merger, Our local group will be alone. The combined galaxy will contain all the stars from both the Milky Way and Andromeda, along with the smaller galaxies in the group. And that will be all. No other galaxies will be visible. No other sources of light. The universe, from the perspective of an observer in that galaxy, will appear to contain only one galaxy. This is the consequence of acceleration, isolation, fragmentation, darkness. The universe is moving toward a state where each gravitationally bound structure, each local group of galaxies, becomes its own universe, cut off from all others. And then there's the consequence for life. Complex life requires stars, planets, and time. Stars provide energy. Planets provide a stable environment. Time allows evolution. But in the far future, all three will become scarce. Stars will burn out. Planets will be lost as their stars die or drift away. Time will stretch on, but without stars, without energy, life as we know it will be impossible. The universe will become inhospitable, not through any catastrophic event, but through the slow, patient work of expansion. This doesn't mean life is doomed in the near future. We have trillions of years before star formation ceases in our galaxy. Civilizations could rise, explore, and flourish for timescales unimaginable to us. But eventually, the expansion will win. The stars will fade. The universe will grow dark and cold. The consequence of the accelerating expansion is not immediate. It's not something we need to worry about in our lifetimes, or even in the lifetime of our species. But it's real. It's the long-term fate of the universe, shaped by dark energy and the relentless stretching of space. Galaxies drifting into darkness, islands of light becoming isolated, the cosmos fragmenting into unreachable pieces. This is the future, written in the mathematics of expansion, confirmed by observations of distant supernovae and the cosmic microwave background. And it brings us back to the question, will the universe stop expanding? The consequences suggest it won't. The drift has begun, the isolation is accelerating, and unless dark energy changes, the universe will continue on this path, growing larger, emptier, colder, until all that remains is a vast dark expanse, where nothing new can happen, and nothing old remains. This is the consequence. This is the price of expansion, and understanding it helps us see not just where the universe is going, but what it means to live in a cosmos that's finite, temporary, and headed toward an end. The discovery that the universe is accelerating didn't just change cosmology, it changed how we see ourselves, our place in time, and the meaning of existence in a cosmos with a predetermined fate. For most of human history, we assumed the universe was eternal and unchanging. The stars would shine forever, the cosmos would endure. There was comfort in that permanence, a sense that even if individual lives were fleeting, the universe itself was stable, reliable, a stage that would last forever. But the accelerating expansion shattered that assumption. The universe has a history, and it has a future, and that future, at least as we currently understand it, is not eternal stability. It's expansion, acceleration, darkness, and cold. The stars will die. The galaxies will drift apart. The universe will become a vast, empty, frozen expanse. This realization had an impact on science first. It forced physicists to confront dark energy, a component of the universe that dominates its fate but remains almost completely mysterious. It motivated new missions, new telescopes, new theoretical frameworks. It became one of the central questions in modern physics. What is dark energy, and what will it do? but the impact extended beyond science. Philosophers began to grapple with the implications. If the universe will eventually become lifeless and dark, does that mean existence is ultimately meaningless? If everything we build, everything we create, everything we are, will eventually be erased by the expansion, what's the point? Some found this conclusion depressing. It seemed to drain meaning from life, to suggest that in the long run, nothing matters. But others saw it differently. The temporary nature of existence doesn't make it meaningless, it makes it precious. A sunset is beautiful precisely because it doesn't last. A song has meaning because it ends. Life has value because it's finite. And even if the universe's ultimate fate is darkness and cold, that's trillions of years away. In the meantime, there's structure, complexity, life, consciousness, beauty. The universe is not dead yet. It's vibrant, dynamic, full of possibilities. Living in an accelerating universe doesn't mean giving up. It means appreciating what we have while we have it. The impact also reached popular culture. Books, films and documentaries explored the fate of the universe, bringing the science to wider audiences. Some portrayed it as a cosmic tragedy, the slow death of everything. Others saw it as an opportunity for wonder, a reminder of how extraordinary it is that we exist at all. In this particular era, when the universe is still full of light, the accelerating expansion also changed how we think about the future of humanity. If the universe will eventually become inhospitable, does that mean our descendants, if any survive that long, are doomed? Or could advanced civilizations find ways to adapt, to harness energy from the last stars, to survive even as the universe grows cold? Some physicists have speculated about far future civilizations that might find ways to slow or reverse local expansion, creating pockets of space where galaxies don't drift apart. Others have proposed that advanced beings might extract energy from black holes, prolonging their existence far beyond the death of stars. These are speculative ideas, bordering on science fiction, but they show that even in a universe headed toward darkness, there might be room for hope. The impact of living in an accelerating universe is also personal. It affects how we see our own lives. We're living in a particular moment in cosmic history, a moment when the universe is still young, still bright, still full of galaxies and stars. Billions of years from now, observers, if any exist, will look up and see a much darker sky. They won't have the privilege we have of seeing the full richness of the cosmos. This makes our era special. We're living at a time when the universe is knowable, when we can see distant galaxies, measure the expansion, trace the history back to the Big Bang. Future civilizations won't have that opportunity. The evidence of the Big Bang will have faded. The distant galaxies will have disappeared. They'll be isolated, with no way to learn about the larger cosmos. We're also living just after the turning point, when dark energy began to dominate. We're witnesses to the transition, able to study a universe in the process of change. This is a privilege, an accident of timing, but it's real. The impact of the accelerating expansion also touched religion and spirituality. Some saw it as consistent with teachings about the impermanence of all things. The universe, like everything in it, is temporary. It arises, it changes, it ends. This is the nature of existence. Others struggled with it, finding it difficult to reconcile with beliefs about eternal creation or divine plan. But across different perspectives, there was a common thread. Recognition that the universe is not what we thought. It's not eternal. It's not static. It's evolving, accelerating, heading toward a fate that's very different from its past. And that challenges us, not just scientifically, but existentially, to find meaning in a cosmos that will one day go dark. Living in an accelerating universe means living with uncertainty. We don't know if dark energy will remain constant. We don't know if the expansion will continue forever, or if something will change. We don't know if future civilizations will find ways to survive, or if life is a temporary phenomenon destined to fade when the stars burn out. But uncertainty is not the same as meaninglessness. The fact that we don't know the future doesn't mean the present doesn't matter. In fact, it might mean the opposite. If the future is uncertain, then what we do now, how we live, what we create, becomes more important, not less. The impact of the accelerating expansion is ongoing. It's shaping science, philosophy, culture, and how we see ourselves. It's a reminder that we're part of something larger, a universe that's ancient, vast, and evolving. And it's a call to pay attention, to appreciate the moment we're in, to recognize that we're living in a special time when the cosmos is still knowable, still full of wonder. The universe is accelerating, galaxies are drifting apart, the future is uncertain, but we're here, now, able to see it, to measure it, to ponder what it means. And that's not nothing, that's everything. Behind every measurement, every equation, every telescope pointed at the sky, there are people, dreamers who dedicated their lives to understanding the universe's fate. Their stories are part of the story of expansion, part of the human quest to know what comes next. Edwin Hubble was one of the first. In the 1920s, working at Mount Wilson Observatory, he measured distances to galaxies and discovered they were receding. He established the relationship between distance and velocity, showing that the universe was expanding. Hubble's work transformed cosmology from philosophy to science, from speculation to measurement. But Hubble didn't know about acceleration. He died in 1953, decades before that discovery. He saw the expansion, but he thought it was slowing down, pulled back by gravity. He never knew that dark energy would take over, that the universe would begin to accelerate. The discovery of acceleration came from two teams of astronomers in the late 1990s. Saul Perlmutter led the Supernova Cosmology Project. Brian Schmidt and Adam Rees led the High-Z Supernova Search Team. Both teams spent years observing distant supernovae, measuring their brightness and redshift, looking for evidence of how the expansion had changed over time. The work was painstaking. Each supernova had to be discovered, observed, analysed. The data had to be checked and rechecked for errors. The teams were competing, racing to publish first, but they were also collaborating, sharing ideas and methods, because the question was too important for rivalries. When the results came in, both teams found the same thing. The expansion was accelerating. It was a shock. Perlmutter later said he spent months trying to find what was wrong with the data before accepting that it was real. Schmidt admitted he didn't want to believe it at first. The result was too strange, too unexpected, but the data held. And in 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for their discovery. Their work had revealed one of the deepest mysteries in science: dark energy. Another key figure was Vera Rubin, an astronomer who studied the rotation of galaxies. In the 1970s, she showed that galaxies rotate too fast to be held together by the gravity of their visible matter alone. There had to be something else, something invisible, providing additional gravitational pull. That something was dark matter. Rubin's work didn't directly reveal dark energy, but it showed that the universe contained unseen components, mysteries hidden in plain sight. It prepared the scientific community for the idea that most of the universe might be made of things we can't see or understand. Then there are the engineers and mission planners who built the instruments to study the universe. The Hubble Space Telescope, launched in 1990, revolutionized astronomy. It provided high-resolution images and spectra free from the blurring effects of Earth's atmosphere. Much of what we know about the expansion comes from Hubble's observations. The Wilkinson Microwave Anisotropy Probe and Planck satellite mapped the cosmic microwave background, revealing the universe's composition and confirming the existence of dark energy. These missions required decades of planning, thousands of people working together, and budgets in the billions. They were massive collaborative efforts, testaments to what humanity can achieve when we work toward a common goal. There are also the theorists who developed the mathematical frameworks to understand the expansion. Albert Einstein, who formulated general relativity in 1915, initially added a cosmological constant to his equations to keep the universe static. When Hubble discovered the expansion, Einstein called the cosmological constant his biggest blunder and removed it. But decades later, when acceleration was discovered, the cosmological constant came back. It turned out Einstein's blunder was actually a prediction of dark energy. The constant he added to keep the universe static was the same force driving it to accelerate. Einstein didn't live to see this vindication. He died in 1955. But his equations were flexible enough to accommodate the discovery. Other theorists, like Stephen Hawking, Roger Penrose, and André Linde, developed models of the universe's origin and fate. They explored singularities, black holes, inflation, and the multiverse. Their work provided the conceptual tools to think about deep time, about timescales of trillions or googles of years, about the ultimate fate of everything. And then there are the students, the postdocs, the early career scientists who are working on these questions right now. They're analyzing data from the latest telescopes, developing new theories, planning new missions. The investigation of dark energy is ongoing, and the next generation of astronomers will carry it forward. But the human element isn't just about famous scientists. It's also about the countless people who built the telescopes, wrote the software, maintained the observatories, taught the classes, inspired the students. Science is a collective endeavour built on the work of thousands of people, most of whom never become famous, but all of whom contribute. And it's about you, the listener, by wondering about the universe's fate, by asking whether it will stop expanding. You're part of the human quest to understand the cosmos. You don't need a PhD or a telescope to be part of this. Curiosity is enough. Wonder is enough. The dreamers at the edge of time are not just scientists. They're anyone who looks up at the night sky and asks what comes next. Anyone who ponders the fate of the stars, the future of galaxies, the meaning of existence in an expanding universe. You're one of those dreamers. The human element is what makes the question personal. It's not just an abstract puzzle about dark energy and cosmology. It's a question about our place in time, about whether we're living in a special era, about what it means to exist in a universe that's accelerating toward darkness. The people who studied the expansion, who measured it, who discovered acceleration, were driven by curiosity. They wanted to know. And their work has given us a glimpse of the future, a map of where the universe is going, even if we don't yet know all the details. But their work also raises new questions. What will future generations discover? Will they find that dark energy changes, that the expansion slows or reverses? Will they develop technologies to probe deeper into the mystery? Or will they be limited by the isolation that acceleration brings unable to see beyond their local group of galaxies. The dreamers at the edge of time are still dreaming. The quest continues, and as long as humans exist, as long as we look up and wonder, the human element will remain at the heart of the story. We are the universe trying to understand itself. And through the work of dreamers, through their dedication, their curiosity, their willingness to spend decades staring at distant supernovae or analyzing faint signals from the edge of space, we've learned something profound. The universe is expanding, accelerating, heading toward a fate that's both beautiful and tragic. The human element is hope. Hope that we can understand, even if we can't change the outcome. Hope that the act of understanding is itself meaningful, even in a universe that will one day go dark. Hope that by asking the question, by pursuing the answer, we're doing something important, something that matters, even if only for a brief moment in cosmic time. For all our progress in understanding the universe's expansion, there remains a fundamental opposition, a barrier that limits what we can know and what we can do. The opposition is not hostile. It's not an enemy. It's simply the nature of the cosmos itself. The vast distances, the time scales, the speed of light, and the acceleration that's carrying most of the universe beyond our reach. The first opposition is distance. The observable universe is about 93 billion light-years across. That's the region from which light has had time to reach us since the Big Bang. But most of the universe lies beyond that horizon. We can't see it, can't observe it, can't study it. It's forever inaccessible. And as the universe accelerates, the observable universe will shrink. Galaxies that are currently visible will drift beyond the horizon. In 150 billion years, only our local group will remain visible. Everything else will be gone, hidden beyond the expanding edge of space. This creates a practical limit on what we can know. We can only study what we can see. And as more of the universe disappears from view, we lose information. Future cosmologists won't have the data we have. They won't be able to measure the expansion rate across billions of light-years. They won't be able to see the cosmic microwave background. Their view of the universe will be limited, incomplete. The second opposition is time. The timescales on which the universe evolves are incomprehensibly long. The universe is 13.8 billion years old. That's already longer than the human mind can fully grasp. But the universe's future, if dark energy remains constant, extends for trillions, quadrillions, googles of years. Stars will die, galaxies will fade, black holes will evaporate, all on timescales that make the current age of the universe seem like an eye blink. And we, living in this brief moment, can only observe a tiny fraction of that timeline. We're like mayflies, born at dawn, trying to understand the life cycle of a tree. This temporal opposition limits our ability to test theories. We can observe the universe as it is now, and we can look back in time by observing distant galaxies. But we can't observe the future. We can only predict, based on models, based on assumptions about dark energy that might be wrong. The third opposition is the speed of light. Nothing can travel faster than light, and light itself takes time to cross cosmic distances. The light from the most distant galaxies we can see has been travelling for over 13 billion years. By the time it reaches us, those galaxies have moved farther away, carried by the expansion. We're not seeing the universe as it is, but as it was. This creates a fundamental disconnect. The present moment, now, is not the same everywhere in the universe. Our now is here on Earth, but a distant galaxy's now is billions of years offset from ours due to the light travel time. We can never observe the universe as it is simultaneously everywhere. We're always looking at a patchwork of different times, stitched together by light that's been travelling for varying durations. The fourth opposition is the isolation that acceleration brings. As galaxies drift beyond the horizon, they become permanently isolated. No signal from them will ever reach us. No communication will ever be possible. Each gravitationally bound region of space becomes its own island universe, cut off from all others. This means that even if life exists in other galaxies, even if civilizations arise and flourish, we'll never know. They're beyond our reach, beyond our ability to observe or communicate with. The accelerating expansion is creating a universe of isolated pockets, each unaware of the others. The fifth opposition is philosophical. We want to understand the universe's fate, but we're embedded in it. We're not outside observers looking in. We're inside, part of the system we're trying to understand, and our perspective is limited by our location, our time, and our tools. We can measure the expansion rate here and now, but we can't measure it everywhere. We can infer what's happening in distant regions, but we can't confirm it. We can predict what will happen in the future, but we can't observe it. We're trying to understand an entire universe from a single point in space and time, like trying to understand an ocean by looking at a single drop of water. The sixth opposition is uncertainty. We don't fully understand dark energy. We don't know if it's constant or changing. We don't know if our models are correct or if there's something we're missing. Every prediction about the universe's fate comes with caveats, assumptions, uncertainties. And small uncertainties now can lead to vastly different outcomes in the far future. If dark energy weakens slightly, the universe might eventually recollapse. If it strengthens slightly, the universe might tear itself apart in a big rip. The difference between these scenarios is tiny in terms of dark energy's properties, but enormous in terms of consequences. The seventh opposition is existential. The accelerating expansion suggests a future that's dark, cold, and empty. This is hard to accept emotionally. We want the universe to be permanent, to endure, to provide a stable backdrop for existence. But the expansion tells us that's not the case. The universe is temporary, evolving, heading toward an end. This creates an opposition between what we want and what is. We want meaning, permanence, purpose. The universe offers change, impermanence, and an indifferent fate. Reconciling these is a challenge, not just intellectually, but emotionally and spiritually. Despite all these oppositions, humans continue to study the universe. We build better telescopes. We develop better theories. We push against the limits, trying to see farther, measure more precisely, understand more deeply. The oppositions are real, but they're not insurmountable. They're challenges, problems to solve, barriers to overcome. But some barriers might be fundamental. We might never fully understand dark energy. We might never see beyond the cosmic horizon. We might never know for certain what the universe's fate will be. The silence ahead, the vast unknown, is part of the reality we live in. And perhaps that's okay. Perhaps not knowing is part of the human condition. Perhaps the quest to understand, even if we never reach complete understanding, is itself meaningful. The opposition is real, but it's also an invitation to keep exploring, keep wondering, keep asking questions, even when the answers are elusive. The silence ahead is not an ending. It's a frontier, a boundary beyond which our knowledge fades, but our curiosity remains. And as long as we keep looking, keep measuring, keep dreaming, We're pushing back against that silence, illuminating a little more of the darkness, understanding a little more of the cosmos. There comes a moment in contemplating the universe's expansion when understanding shifts from intellectual to visceral. When you realize deeply that you're not separate from this process, you're part of it. The expansion is not something happening out there in distant galaxies. It's happening through you, around you, because of you. This is the awakening, the recognition that you are woven into the fabric of an expanding cosmos, not metaphorically, but literally. Start with the atoms in your body. Every atom heavier than hydrogen and helium was created inside a star. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all were forged in stellar cores through nuclear fusion. When those stars died, they released those atoms into space, where they drifted for millions of years before being incorporated into new stars, new planets, eventually into you. The expansion of the universe determined how those atoms got to you. It shaped the timeline of star formation, the distribution of matter, the conditions that allowed galaxies and solar systems to form. If the expansion had been much faster, matter would have spread too thin for stars to form. If it had been much slower, the universe might have recollapsed before planets could arise. The expansion rate is part of the chain of causality that led to your existence. But it goes deeper. The expansion is not just part of your history, it's part of your present. The space around you is expanding. Not in your room, gravity and atomic forces hold everything together on small scales. But between galaxies, between clusters, in the vast cosmic web, space is stretching. And that stretching affects the light that reaches you, the particles that pass through you, the very structure of the cosmos you inhabit. You're living in an expanding universe. Every photon of starlight you see has been stretched by the expansion. Every cosmic ray that passes through your body has been shaped by the magnetic fields in expanding space. The cosmic microwave background radiation, the faint afterglow of the Big Bang, bathes you constantly, and its properties are determined by how the universe has expanded over 13.8 billion years. The awakening also involves recognizing your place in time. You're living in a particular era of cosmic history, a moment when the universe is about 13.8 billion years old, when stars are still forming, when galaxies are still visible, when dark energy has just begun to dominate. You're not living in the early universe, when everything was hot and dense and no stars existed yet. You're not living in the far future, when all stars have died and all galaxies have drifted beyond the horizon. You're living in the middle, in the era when the universe is rich with structure, complexity, and light. This timing is not random. It's part of the anthropic selection. You exist now because this is when conditions allow life. Earlier was too chaotic. Later will be too dispersed. You're here, in this particular cosmic moment, because this is when the universe is capable of producing beings like you. The awakening also brings recognition of impermanence. You are temporary. Your atoms will not stay with you forever. When you die, they'll return to the earth, and eventually, over geological timescales, some might escape into space. They'll rejoin the cosmic cycle, drifting through the expanding universe, perhaps one day becoming part of a new star, a new planet, a new form of life. The expansion will carry your atoms forward. They'll participate in the universe's ongoing evolution, even after you're gone. In that sense, you're not just part of the expansion now, you're part of it forever. Your atoms are travelers in an expanding cosmos, and their journey will continue long after your brief arrangement of them dissolves. This realization can be unsettling. It reminds you of your smallness, your fragility, your temporary nature. But it can also be liberating. You're not separate from the cosmos. You're part of its unfolding. You're not a static thing, but a process, a pattern, a brief moment in the larger flow of existence. The awakening also changes how you see the expansion itself. It's not a cold, mechanical process. It's the breath of the universe. The cosmos inhales, gathers matter, creates stars and galaxies. It exhales, disperses energy, expands space, and you, living within that breath, are part of the rhythm. When you breathe in, you're bringing atoms from the atmosphere into your body. Those atoms were once in plants, in the ocean, in the soil. They've travelled through the biosphere, cycling endlessly. And before that, they were in space, part of the interstellar medium, shaped by the expansion of the universe. When you breathe out, you're releasing atoms back into the environment. Carbon dioxide that will be absorbed by plants. Water vapour that will join the atmosphere. Those atoms will continue their journey, moving through the Earth's systems, and eventually, on timescales far longer than human lifetimes, some will escape and rejoin the cosmos. Your breath is part of the universe's breath. The expansion is the largest breath, the slowest exhale, and within it, smaller breaths occur. The breath of galaxies, of stars, of planets, of life, all nested within each other, all part of the same cosmic process. The awakening is recognizing this connection. It's seeing that the question, will the universe stop expanding, is not just about distant galaxies or dark energy. It's about the future of everything, including you. Not your individual future. You won't be around to see the universe's ultimate fate. But the future of the pattern you're part of, the ongoing process of existence. And it's recognizing that even though the universe might expand forever, even though it might grow cold and dark, that doesn't make your existence meaningless. You're here, now, part of the breath. You're a way for the universe to know itself, to experience itself, to reflect on its own expansion. And that, in itself, is extraordinary. The awakening is not a one-time event. It's a deepening awareness that grows with contemplation. Each time you think about the expansion, each time you look up at the night sky, each time you wonder about the future, the awakening deepens. You see new connections, new meanings, new ways in which you're woven into the cosmos. You are part of the breath. The universe is breathing, expanding, unfolding, and you, for this brief moment, are part of that process. Not separate, not outside, but integrated, essential, a temporary arrangement of atoms that can think and feel and wonder about the expansion itself. This is the awakening, the recognition that you belong to an expanding universe, that you're made from its material, shaped by its history, and participating in its ongoing evolution. And once you've had that awakening, you can never see yourself, or the universe, the same way again. After all the data, all the theories, all the exploration of dark energy and cosmic fate, there's one final revelation that brings everything together. It's simple, yet profound. The universe doesn't just expand out there in the vastness of space. It expands within you. This isn't poetry. It's not metaphor. It's a recognition that the processes shaping the cosmos, expansion, evolution, transformation, are the same processes shaping you. The universe and you are not separate things. You are what the universe is doing in this particular place, at this particular time. Consider your body. It's not a fixed object. It's a process. Every cell is constantly being rebuilt. The atoms that make up your cells are constantly exchanged with the environment. You eat, you breathe, you drink, and new atoms enter your body. You exhale, you excrete, you shed skin, and atoms leave. Over the course of a few years, almost every atom in your body is replaced. You are a pattern maintained by a flow of matter and energy. You're not a thing, but a happening. A temporary arrangement that persists through constant change. And that pattern, that process, is part of the universe's larger pattern, its ongoing expansion and evolution. The universe is doing the same thing on a grander scale. It's not a static object, it's a process. Space is expanding, galaxies are moving, stars are forming and dying. The cosmos is in constant flux, constantly changing, constantly becoming something new. And you, as part of that cosmos, share that quality. You're in flux, you're changing, you're becoming. The expansion of the universe is also an expansion of possibility. When the universe was young, shortly after the Big Bang, it was simple, just hydrogen and helium, spread almost uniformly. But as it expanded and cooled, complexity emerged. Gravity pulled matter together. Stars formed, heavy elements were created, galaxies clustered, planets arose, and eventually, on at least one planet, life emerged. Expansion allowed this complexity. If the universe had remained small and dense, nothing interesting could have happened. Everything would have stayed uniform, hot and chaotic. But expansion created space for diversity, for structure, for the slow work of gravity and chemistry to create new forms. You are one of those new forms. You are an expression of the universe's expanding complexity. The atoms in your body have been through countless transformations. They've been part of stars, part of interstellar clouds, part of planets, part of other living things. And now they're part of you, arranged in a pattern so complex that it can think, feel, and contemplate its own origins. This is the universe expanding into awareness. For most of its history, the universe existed without knowing it existed. Stars shone, galaxies formed, but there was no consciousness, no awareness, no entity capable of asking, "What am I?" Then, at some point, complexity reached a threshold. Life emerged. And eventually, from life came consciousness, beings capable of reflecting on their own existence and the existence of the cosmos. You are one of those beings. You are the universe become aware of itself. When you look up at the night sky and wonder about the stars, the universe is looking at itself. When you ask whether it will stop expanding, the universe is asking about its own fate. You're not separate from the cosmos, observing it from outside. You're part of it, a way for it to know itself. The revelation is that the expansion is not just a physical process. It's also an expansion of consciousness, of understanding, of the universe's self-awareness. Each discovery, each insight, each moment of wonder is the universe learning about itself through you. And this process continues. Right now, as you listen, new thoughts are forming in your mind. Neural connections are being made, strengthened, reorganized. Your understanding is deepening. And that's not just your individual growth, it's the universe's growth. The cosmos is expanding not just spatially, but also in its own self-knowledge, through the minds of conscious beings like you. The expansion within you is also about potential. You're not fixed. You can change, grow, evolve. Your thoughts can expand. Your understanding can deepen. Your compassion can widen. Every moment offers the possibility of becoming something more than you were. This mirrors the universe's expansion. The cosmos is not reaching a final state. It's constantly unfolding, constantly revealing new possibilities. As space expands, new configurations of matter become possible. New structures can form, new complexities can emerge. The universe is open-ended, and so are you. But there's also a poignant aspect to this revelation. Just as the universe's expansion might lead to darkness and cold in the far future, your own expansion, your own growth, is temporary. You will die. Your pattern will dissolve. The atoms that make you up will be dispersed. But here's the profound part. Those atoms will continue. They'll rejoin the universe's ongoing process. They'll be part of new patterns, new forms, new possibilities. Your particular arrangement is temporary, but the atoms themselves and the potential they carry are eternal. The universe's expansion within you means you're part of an ongoing cycle. You're not an endpoint. You're a chapter in a much longer story. The universe was expanding before you existed, creating the conditions that allowed you to be. And it will continue expanding after you're gone, carrying your atoms forward into new configurations. This is not sad. It's simply the nature of existence. Everything is temporary, everything changes. But everything is also connected, part of the larger flow. You're not isolated. You're integrated into the cosmic process, a wave in the ocean of existence. The revelation is that when you ask, will the universe stop expanding? You're really asking about yourself. Will the process you're part of, the unfolding of existence, ever stop? And the answer, at least as far as we can tell, is no. The expansion continues, the universe keeps unfolding, and even after your individual pattern dissolves, the larger pattern continues, carrying forward the potential for new forms, new awareness, new expressions of cosmic complexity. You are not separate from the expansion. You are the expansion. You are what it looks like when the universe expands into consciousness, into awareness, into the capacity to ask questions about itself. The expansion is not happening to you, it's happening through you. You are the universe's way of expanding beyond mere matter and energy into thought, feeling, and understanding. This is the final revelation. The universe doesn't just expand in space, it expands in complexity, in awareness, in meaning. And you, right now, are part of that expansion. You are the universe still expanding within itself, discovering itself, becoming more of what it always had the potential to be. And that continues. The expansion within you doesn't stop when you breathe your last breath. It continues through the atoms. You return to the cosmos, through the ideas you shared, through the love you gave, through the ripples you created in the lives of others. The expansion is eternal, and you're part of that eternity. Now that we've journeyed through the expanding universe, through dark energy and distant galaxies, through the fate of the cosmos and our place within it, what does it all mean? What does it mean to exist in a universe that's drifting apart, accelerating toward isolation, heading toward darkness and cold? This is where the scientific journey gives way to reflection, where data transforms into meaning, where cosmology becomes philosophy. First, there's the meaning of scale. The universe is incomprehensibly vast. The distances between galaxies are measured in millions or billions of light years. The timescales of cosmic evolution are measured in billions or trillions of years. Compared to these scales, human life is infinitesimally small. You live for decades on a planet that's existed for billions of years, in a universe that will exist for trillions more. This scale can feel crushing. It can make you feel insignificant, powerless, lost in the immensity. But there's another way to see it. The fact that you exist at all, that you're here to contemplate these scales, is extraordinary. Against all odds, the universe arranged itself in such a way that consciousness emerged, that beings arose who could ask questions about expansion and fate. You're not insignificant. You're the universe's way of knowing itself. Second, there's the meaning of impermanence. Everything in the universe is temporary. Stars are born and die. Galaxies form and disperse. Even the universe itself, if current models are correct, will eventually reach a state of maximum entropy, where no energy is available to do work, where nothing can change. This impermanence extends to you. You're temporary. Your thoughts, your feelings, your relationships, all temporary. And in the face of that, it's easy to fall into nihilism, to think that nothing matters because it all ends anyway. But impermanence doesn't erase meaning. It creates meaning. A sunset is beautiful precisely because it's temporary. A relationship is valuable because it won't last forever. Life has meaning because it's finite. The expansion of the universe, heading toward darkness, doesn't make existence meaningless. It makes the time we have more precious. Third, there's the meaning of connection. The expansion is separating galaxies, creating isolation on cosmic scales. Eventually, galaxies beyond our local group will drift beyond the horizon, disappearing from view. The universe is fragmenting, breaking into unreachable pieces. But right now, in this moment, we're still connected. The light from distant galaxies still reaches us. The cosmic microwave background still carries information about the universe's past. We can still see, still measure, still understand the larger cosmos. And that connection, however temporary, is meaningful. On a more personal level, connection is what makes life worthwhile. Relationships with others, with nature, with the cosmos itself. These connections are temporary, shaped by the flow of time and the expansion of the universe, but they're real, and they give life meaning. Fourth, there's the meaning of curiosity. The question, will the universe stop expanding, is driven by curiosity, by the desire to understand. And that curiosity, that quest for knowledge, is itself meaningful. It's what separates humans from most other forms of life. We don't just survive. We wonder. We ask questions. We seek to understand. And the pursuit of understanding is its own reward. Whether or not we fully answer the question, whether or not we ever completely understand dark energy, the act of asking, of exploring, of pushing against the boundaries of knowledge is meaningful. It's part of what makes us human. Fifth, there's the meaning of perspective. Understanding the universe's expansion gives perspective on our own lives, our own problems, the things we worry about, the conflicts we get caught up in, the anxieties that consume us. They're real and important on a human scale, but on a cosmic scale, they're fleeting. This doesn't mean they don't matter. It means that we can hold them lightly, with less attachment, with more compassion. The universe is vast, and we're small, but that smallness can be liberating. It can free us from the weight of our own self-importance, allowing us to see ourselves as part of something larger. Sixth, there's the meaning of participation. You're not just observing the universe's expansion, you're participating in it. Every breath you take, every thought you think, every action you perform is part of the cosmic process. You're not separate from the expansion, you're embedded in it, shaped by it, contributing to it. This participation is meaningful. It means your existence is not arbitrary. You're here because the universe unfolded in a specific way, because stars formed and died, because galaxies clustered, because a planet with the right conditions arose. You're part of the story, a chapter in the universe's ongoing narrative. Seventh, there's the meaning of acceptance. The universe's fate, as far as we can tell, is determined by dark energy. If dark energy remains constant, the expansion will continue forever. Galaxies will drift apart. Stars will die. The universe will grow dark and cold, and there's nothing we can do about it. This requires acceptance, not resignation, but acceptance. Recognition that the universe unfolds according to its own laws, its own patterns, independent of our wishes. We can understand it, we can measure it, but we can't control it, and that's okay. Acceptance allows us to focus on what we can influence, our own lives, our own actions, our own small corner of the cosmos. Finally, there's the meaning of wonder. Despite everything we've learned, despite all the data and theories, the universe remains fundamentally mysterious. Why is there something rather than nothing? What is dark energy? What lies beyond the cosmic horizon? Will the expansion ever stop? These questions inspire wonder, that feeling of awe in the face of something vast and incomprehensible. And wonder is meaningful. It connects us to the cosmos, reminds us that we're part of something larger, something older, something that will continue long after we're gone. To drift, then, is to accept impermanence while finding meaning in the present, to recognize that you're part of an expanding universe, carried along by forces beyond your control, yet still capable of thought, feeling, and action. To see yourself as both infinitesimally small and profoundly significant. To live with the tension between knowing the universe will end and choosing to create meaning anyway. The expansion continues. Galaxies drift apart. The universe grows larger. And within it, you exist, briefly, asking questions, seeking understanding, finding connection, creating meaning. That's what it means to drift. And so we return, gently, to where we began, to the stillness of the night, to the quiet breath of the cosmos, to you lying there, part of an expanding universe. You've travelled with me through the discovery of expansion, through the mystery of dark energy, through the theories of the universe's fate. You've learned that the cosmos is not static, but dynamic, accelerating toward a future that's vastly different from its past. You've seen that most of the universe is made of something we don't understand, that dark energy dominates the cosmos, that galaxies are drifting apart into isolation. And you've learned something deeper, that you're not separate from this process. You're part of it, made of atoms forged in stars, shaped by billions of years of cosmic evolution, living in a particular moment in the universe's story. You are the universe looking at itself, asking questions about its own fate. The question we explored, when will the universe stop expanding, has an answer, at least provisionally. No, it probably won't stop. If dark energy remains constant, if current models are correct, the expansion will continue forever. Galaxies will drift beyond the horizon, stars will burn out. The universe will grow dark and cold, expanding toward a state of maximum entropy, where nothing new can happen. But that's trillions of years away. Right now, the universe is still full of light, still full of galaxies and stars, still full of possibility. You're living in a special time, cosmologically speaking, when the cosmos is knowable, when we can see distant galaxies and measure the expansion, when the sky is still bright with starlight. And even if the expansion never stops, even if the universe is heading toward darkness, that doesn't make existence meaningless. You're here now. You're conscious, capable of wonder, able to contemplate the cosmos and your place within it. That's extraordinary. That's the universe becoming aware of itself through you. The expansion will continue. But so will you, for now. The atoms that make you up will persist long after your individual pattern dissolves. They'll rejoin the cosmic cycle, drifting through the expanding universe, perhaps one day becoming part of new stars, new planets, new forms of existence. The expansion carries everything forward, including you. As you lie there now, in the quiet of your room, in the stillness of the night, imagine yourself floating gently through space. Not physically, but in your mind. You're drifting between galaxies, surrounded by the thin fabric of expanding space. Around you, galaxies are receding, carried by the slow, patient stretching of the cosmos. But you're not alone. You're part of the universe, woven into its structure, connected to everything through the atoms you share. The light you receive, the same physical laws that govern stars and planets, and the expansion itself. You're drifting, but you're not lost. You're where you're supposed to be, part of the cosmic flow. The question of whether the universe will stop expanding is, in some ways, less important than the act of asking it. The curiosity, the wonder, the desire to understand, these are what make us human. These are what make the universe's awareness of itself possible. And as long as consciousness exists, as long as beings arise who can look up and wonder, the universe continues to expand in meaning, in self-knowledge, in understanding. The quiet returns now. The stillness of the cosmic night, the slow breath of expansion. You're part of that stillness, connected to it, made from it. And as your own thoughts slow, as your breathing deepens, as you drift towards sleep, you can rest in the knowledge that you're part of something larger, something ancient, something that will continue long after you're gone. The universe is still expanding. Space is still stretching. Galaxies are still drifting apart. And within it all, briefly, you exist. A temporary arrangement of atoms, a fleeting pattern in the cosmic flow, but also a moment of consciousness, of awareness, of the universe knowing itself. When will the universe stop expanding? Perhaps never. But the expansion is not just about distance and darkness. It's about unfolding, about becoming, about the ongoing revelation of what the cosmos is and what it can be. And you're part of that revelation. Before you sleep, before you let go of these thoughts and drift into your own darkness, take a moment to feel the connection. Feel yourself as part of the expanding universe, not separate, not outside, but woven into the fabric of existence. You are stardust. You are cosmic dust. You are the universe, briefly arranged into a form that can think and feel and wonder. The expansion continues. The universe grows larger. Galaxies drift into darkness. But the process that created you, the cycle of matter and energy through time and space, that continues too. You're part of that cycle, and in being part of it, you participate in the universe's ongoing story. The quiet returns, the stillness holds you, and in that stillness there's a kind of peace, not the peace of answers, but the peace of acceptance. The universe is what it is. It expands, it evolves, it becomes, and for this brief moment, you're part of that becoming. Welcome home, wanderer. Welcome home to the expanding cosmos. You've always been part of it. You always will be. The atoms that make you are eternal, even if your pattern is temporary. And as you drift now towards sleep, toward dreams, toward the quiet darkness behind your closed eyes, remember that you're drifting through an expanding universe, carried along by the same forces that move galaxies, shaped by the same history that created stars. The universe still expands, and so do you, in every breath, in every thought, in every moment of wonder. You are the expansion made conscious. You are the cosmos, aware of itself. You are part of the ongoing story, the endless unfolding, the patient, quiet breath of everything that is. Rest now. The expansion continues, and you, for this brief, beautiful moment, are part of it. Good night.